Good afternoon, everyone, and welcome to our weekly MCube seminar. It's my pleasure to introduce our seminar speaker today, Professor Suzana Camargo. She joined us from Lamont-Doherty Earth Observatory from Columbia University, where she is the Mary Tharp Lamont Research Professor and also an adjunct professor in the Department of Earth and Environmental Sciences. Suzana is originally from Brazil, where she studied physics at the University of Sao Paulo. She then went to Germany, where she did research at the Max Planck Institute for Plasma Physics and got her PhD also in physics from the Technical University of Munich. She stayed there at MPI for a postdoc before moving back to Brazil, where she was an associate professor of physics at the Sao Paulo State University. And then she moved to Columbia University since 1999, where she works on various topics related to tropical cyclones, climate science, and risk analysis. Suzana is a co-author of over 170 published papers. She's also an editor for GRL, a member of two AMS committees, and a recipient of several awards. And although I haven't had the chance of work scientifically with Suzana, I've met her over the years, and she's a strong advocate for women and Latinas in the atmospheric sciences community, something I'm very thankful for. So we welcome Suzana today. She's going to talk to us about tropical cyclone projections using environmental proxies and statistical-dynamical downscaling.
Hello, thanks for coming. It's nice to see so many people in person here. At Columbia, we're still struggling to have everybody come to the seminars in person. Thanks, Rosie, to hosting me here this week. It has been a long time since I have been to NCAR. I'm going to talk about tropical cyclone projections. Lots of collaborators, a lot of the work here I'm doing, it's with my group at Columbia and all kinds of collaborators. So I thank them all. I hope I put their names in the right places. So what I thought I would start with is with a review of tropical cyclones and climate, what we know. And the reason I decided to start with that is because I have been involved in multiple assessments recently. So I have been on top of that. And then, so the first part is really review and recent assessments and see what we know. And then I start then talking about my recent work and work that my group has been doing and with the conclusions. So what do we know about tropical cyclones and climate in terms of projections? So this paper that was led by Tom Knutson, and I was one of the co-authors, this figure, which I think has a big summary, what we know now, and most of these things we've known for a long time. So that's one of the things I want to emphasize. A lot of what we know about the projections have been the same over and over and over again. So, for instance, here is the summary globally, which are the most robust projections. So what we expect in the future, we expect an increase in the intensity of the storms, in particular, the most intense storms. We expect to have more rain associated with tropical cyclones. So these are projections that we have been doing for, decades at this point. What is the most big uncertainty? And I think is the uncertainty that I'm coming back over and over again. That's something that changed over the last 5 years. If you ask me 5 years ago, what are the projections in terms of number of tropical cyclones? We are going to say going to have fewer tropical cyclones in the future. And the time we did this study with Tom, we still have most of the models projecting fewer tropical cyclones globally, but we do have some that are projecting an increase. And so actually the uncertainty in terms of the number of tropical cyclones has increased in the last 5 years or so. And that, I think, is one of the hottest topics that we have in this, people are working on now And if you are a young scientist, maybe it's something that you want to tackle on. And if you look at different basins, the uncertainties are much bigger than globally. So if you want now to do the projections for the Atlantic or for the Indian Ocean, then your uncertainty will be much bigger as you expect. So basically, this is a summary of the tropical cyclone projection for Knudsen. That's what I just said. And basically, the frequency of the tropical cyclones, the main change that I think from the Knudsen paper from 2010, that was not such big uncertainty. And the other one I didn't mention is this poleward shift, especially in the Western North Pacific, that we expect in the future. Another point that we talked in the Knudsen paper, it is not part of that figure, is about storm surge projections. And so here I just put two recent papers. So we have the effect of both increase in sea level rise and tropical cyclone characteristics change. So if you have more intense storms, larger storms, change in translation speed, that will also change your storm surge. And these two papers show the combination of how it changes if you just consider sea level rise, and if you consider sea level rise plus the changes in the storm. So if you just sea level rise, you have a certain amount and increases storm surge, and if you consider sea level rise plus change in the tropical cyclone characteristics, you have even more storm surge. So these are the very robust projections that we have had in a long time. This is when, the chapter 11 on extremes of the IPCC that I also participate. That's what we basically we are saying, that we are having an increase in the intensity of the storms. And here is the uncertainty, the number of tropical cyclones. We don't know if it's going to decrease, stay the same, or increase. The shift in poleward shift in the tropical cyclones. And here we put also having this longer, slower storms like Harvey. That's another point that we decided to highlight on the IPCC chapter. And then in December, there was the IWTC workshop. It's a workshop organized by the WMO and happens every 4 years. It's a summary of everything that we basically know, and tropical cyclones is a combined workshop for researchers and for forecasters. And we prepare a report before the workshop, and this is the team that Hiro Murakami and I led. And we try to discuss what happened in tropical cyclones and climate change in the last 4 years. And the report that we wrote is now in press in this journal, Tropical Cyclone Research and Review, in a special issue for the IWTC. So this is basically what we have from the last 4 years. That's what the IWTC looks at, what changed, what new results appear in the last 4 years. So here's the part of historical and satellite data, which I didn't talk before because it's basically the same sense. So what's very important, and people have to be very careful, that the tropical cyclone records are not consistent, and they have lots of problems in the data pre-satellite era. So any trends that you look and you're using pre-satellite era data, you have to be very careful, because that could be just technological changes. Just because you don't have satellite data, you didn't know there was a storm there. Even then, between 1970 and 1990, there is a lot of issues, especially in the southern hemisphere in the Indian Ocean. So really, we are talking about reliable tropical cyclone records starting in the 1990s. And Phil Klotzbach did a recent paper looking at that period to see which trends we're seeing. And in the global trends in this 30-year period that he looked at, there is a decrease in the annual number of global tropical cyclones, if there's any help with trying to figure out the problem of the frequency in the future. In the present, we are seeing that. There is already an increase in the number of the most intense tropical cyclones, which is one of the projections that we're talking about. But we have to be very careful because we have more of these short-lived storms. These are basically, is that a technological change, a change in policy in the different centers for hurricane centers when they decide to name a storm or count them or not. So that has to be very careful. When we look at the homogenized records from HRSAT, then we can see also an increase in the global tropical intensity and the increased proportion of the most intense tropical storms. And in a follow-up study, they show that this is due to a decrease in the CAT 1 and 2, I have a typo there, and a slight increase in CAT 3 and 5. Using 20th century reanalysis, Savin Shund and a group of quarters where I participated, we find a declining trend in the number of global tropical cyclones in the 20th century reanalysis, which only use surface pressure as input. How well the 20th century analysis has number of tropical cyclones is a big question, but that's what we found. And there is, until now, no trend in global tropical cyclone days. So that's the current state of what we do about current data and what we have seen in terms of trends. What new studies that appear in the last few years? There was these studies by Ralph Toomey and his postdoc that they were looking at the distance of the tropical cyclones to the land, and they found a trend in the location of the maximum intensity of the storms and land. And so they have an increase in the percentage of tropical cyclones that are affecting coastal regions. And that includes the landfalling tropical cyclones and the major tropical cyclones. So they found that trend in the data. I found really interesting, but I would like a physical explanation why this is happening and try to have a dynamical answer of why that's the case, and which it's another, I think, open question that I think we need to explore. If that trend is there, we need to understand why. Another recent result is about the tropical cyclone rainfall trends. As we said, that we have an increase in the tropical cyclone rainfall, but what these studies looked at is that they only see an increase in the outer bands of the rainfall, not in the inner core. In the inner core, actually, they obtain a decrease in the rainfall. That's another question. How can that happen? And I would like to understand. So yes, that's what the satellite data is showing us, but I think we need to understand why that would be the case, why we would have a decrease. They have some explanations, but I think we have in their paper, but they're not, they try to some arguments, but I think we really need to understand why this is the case. And just using Clapeyron is clearly not enough to explain the increases in the rainfall in the outer bands, but why would the core, would be different from the rain bands? I think that's a good problem for people to work on too. And I think a big change that happened in the community is that a few years ago, we would say, we can't do attribution studies for tropical cyclones, and that really changed. Now, there are a lot of attribution studies. We can have studies of past events, like, the Petricola Wenner paper, that they look at a lot of different past cyclones. And then they look at their intensity and rainfall, and they could attribute a slightly increase due to anthropogenic climate change. and also change in the wind structure. But this is really then look at individual cases and running them with and without climate change, pseudo-global warming kinds of studies. And then Kevin Reed, Michael Wenner have been doing these studies in which they actually looking attribution of storms before they actually make landfall. They were making attribution for a storm that make landfall in North Carolina before it actually happened and appear in the news, and now they have done for other storms before they actually happen. And that was attracted a lot of attention of the press, of course, but when they did their first case, there was a lot of criticism because their work had not been peer-reviewed yet. Then they did do a follow-up study and did a peer-reviewed publication of how they do the process. And I think that in the future, we are starting doing like you do operational weather forecasting, you're doing operational attribution of storms. But most of them have been really for the rainfall. They're talking that the rainfall has been increasing due to anthropogenic climate change. And Kevin Reed also has a paper that looking at the full season of Atlantic rainfall and attributed a slightly increase in the most intense rainfall due to anthropogenic climate change. And then Murakami has a very nice paper that look at the patterns and try to do attribution. And what he showed that to do the current patterns and the trends in tropical cyclones, you need to consider aerosols as well, which is, I don't think is a surprise, but he showed very clear with GFDL model, if he's not considering aerosol forcing, he does not get in the current historical patterns correctly. Not only aerosols affecting the Atlantic, but also in Asia as well. It's one model, nice to be done with multiple models and see if that's the case of other models as well, especially representation of aerosols is kind of tricky. Okay. So what's the problem with the frequency of tropical cyclones? We wrote a review paper a couple of years ago about this, and basically that's the story. We do not have a good theory for the number of tropical cyclones. Yeah, we have some constraints, but I don't think we have a good theory that can tell us if we have, why we have about 80 per year and not 8 or 800, right? We can put some constraints about size of the planet and some other things, but I don't think we have a good theory. So if we don't have a good theory, what do we do? We use models. And if the models then give us different answers, with some models increasing the number in the future and some models decreasing in the future, what do we do? So there are lots of promising directions that I think we can go towards that, but I think and there's a lot of people that starting work in this problem. And one of them, one of the ways of doing that is looking idealized simulations, very high resolutions. Another way is to look at percussive disturbance of seeds. People have different way of studying that, and the GFDL group in particular has argued that they look at different models from GFDL, and some of their models were increasing and some were decreasing in the future. And when they took into account the change of the seeds, they could explain why some models increase or some decrease. Basically, if you just look at the changes in the environment and the change, you cannot explain if you're having more or fewer tropical cyclones. But if you also look if that model are having more disturbances in the future, that could lead to more tropical cyclones. Or if they have fewer disturbance in the future, they have fewer tropical cyclones, and then they can explain, they have an index for the seeds, and then they can explain why some models have more in the future and fewer based on the seeds. That's their argument. Of course, it's not always easy. Then Carrie Emanuel, almost a couple, then last year, wrote a paper saying that basically he said that's not explaining the solution of the problem. He's saying provided seeds are defined to be low enough amplitude, the resulting randomly seeded tropical cyclone climatologies appear to be determined entirely by environmental conditions, and of this writing there is no definite evidence that low amplitude weather noise controls tropical cyclone climatology. So basically we have the GFDL group people saying that the seeds are explaining, and Carrie saying he doesn't think that the seeds are explaining. Christina Patricola has two very interesting studies that she and people in her group, they suppress easterly African waves in WRF model. And what was interesting is that when she suppressed the easterly waves, she ended up with the same number of tropical cyclones in the Atlantic. They were just generating a different manner, not through easterly waves, through other disturbances. And she did that now with the convective permitting model as well, and obtained the same result. So I think that's another, these results are really contradicting each other. So I think that's a super hot topic now, and people should really be working on that, especially you guys have all these wonderful models and model simulations. You have the tools to examine some of these questions. So just for people that are not working in this realm, I just want to have a summary. So what are the tools that people use to do tropical cyclone projections? One of them, you go and you track your storms in the model, and you count them and see how intense they are, which is fine. The problem with that is that usually you can't have a lot of ensembles. You can't have the right resolution high enough to have your Cat 4 and Cat 5. There are all these issues with that approach, which people, try to use fixed SSTs or so that the model is not coupled, So that would be, if we could run those models at, an infinite number of ensembles for hundreds of years, that would be our perfect solution. Another one that I have worked a lot with is just doing environmental proxies and try to see how these environmental proxies are relating to in the future, if they change or not. So this is one of the many Genesis index that exist. Genesis index, for those that are not familiar, basically you get environmental variables that that are associated with tropical cyclones, like potential intensity, vorticity, vertical shear, and humidity, and you make get the climatology of that in like reanalysis, and then you have your number of storms in the observations. You do a statistical fit of that. Okay, that's what you're doing. You're doing statistical fit of the mean climatology. So these indices are mostly done to describe climatological features. Okay, and they are derived using reanalysis and observation. So if you change your period of your observations, your statistics is going to change. If you use a different reanalysis, you can do. If you use a different method of your statistical fit, that is all that. When you use them in climate models, which I'm doing right now, I'm assuming that the relationship between the tropical cyclones and the environment is the same in the models than it is between reanalysis and observations. Look that we are not fitting reanalysis storms with reanalysis environmental fields. You're fitting environmental fields with observed tropical cyclones. So that's a big assumption. And then we use for climate change, the further assumption is that we're assuming that that relationship will be the same in the future. Okay? So it's an easy way to work with climate models, but people have to keep in mind the caveats as well. Another way, this I'm going to describe more because we have our own statistical dynamic process at model at Columbia. So basically, you get the environmental fields of either reanalysis or climate models, and you use them to force a statistical model with some physics, depends on which model, Kerry uses, like his hurricane model over the track, but there's some statistics there. And then you produce thousands of storms, and then you can have better statistics to look at risk, but you can also apply over climate change. So this is Kerry's downscaling from the CMIP 5, which is showing an increase in tropical cyclones in the future, as well as similar to what most Genesis index do, they do increase in the future. And then, or you can do dynamical downscaling, which don't have to explain here at the NCAR what dynamic downscaling is. But okay, so all these models have their issues. There is no perfect way of doing that, right? And the high resolution models is the sample size, depends on the resolution. You're not resolving the most intense storms. And Chris Davey has a paper that I mention all the time that he mentions that some models that have resolution that you shouldn't be obtaining Cat 4 and Cat 5, but they're getting that for the wrong reasons. So when you say, look, my model is 25 kilometers and I'm getting Cat 5, you shouldn't be that proud because probably your model is doing something wrong. The dynamical downscaling has all issues, the boundaries, you have, only one basin, you have, you've tried to do extra, so there are all their issues as well. Statistical downscaling, some of the statistical model is a really statistical model. They don't use current climate. If you go like the reinsurance companies, a lot of them, they have their statistical model to generate synthetic tracks, and a plain statistical model cannot handle climate change, or they do very simple assumptions. There is no dynamics, nothing. The statistical dynamic downscaling, there's some dynamics including, but it's not fully simulating the storms. Depends on which statistical dynamic model you're using. And typically you're using monthly fields to download the storms, but does cover the full intensity, and you have a huge number of storms to work with. Okay, what's important here? All this will depend on the environmental fields that you're using. So if I'm counting your storms, I'm doing the Genesis index, or I'm doing downscaling with whatever method, whatever the CMIP 6 or CMIP 5 models are doing, that you're using that's going to influence your answer, okay? So if there are biases there, your answer will be influenced by that. And people never talk about that. So what can we do with that? So we have the Genesis index increasing in the future, and a lot of climate models decreasing, but some increasing, some saying it's the seed. So there are a lot of issues that we have to deal with these projections. And so the uncertainty is large, but that's where we are right now. Okay. One of the issues that I have been working on for a long time is that using the Genesis indices, is that I try to tackle the problem of the fact that most Genesis indices increase in the future, and the number, if you count the storms, in most models decrease in the future. So what I did in my paper a few years ago, I got the high-run model, and using a perfect setup that I train a Genesis index in the model with the model fields and the model tropical cyclones. I tried, what can I do? How can I have, so I had the historical and I have the future, so I had the answer already. I knew, what the model was doing. And what happened was that The only way I use, the typical fields that people use for tropical cyclones to train my Genesis index, and the only way I could have a decrease in the future is what I use, instead of the relative humidity or column relative humidity, I use the saturation deficit as my humidity variable. They do not differ in the present, but these indices have it's very hard to say how one is better than the other in the present, but in the future they have completely different responses. So we try to understand why is that and what to understand, can we solve that? Okay, so I have been looking a lot at the CMIP6 biases in these environmental fields that we use as statistic proxies, and hopefully my paper will be submitted soon. I'm using the standard thing, 45 CMIP models, historical, 3 future scenarios. My requirement that the models have at least to have historical and SSP 585, because some models do not have the other 2 scenarios. I use all ensembles that I can use, and I regrid them to a 2-degree to 2-degree to do the common grid for the environmental fields, and I'm using as my baseline error 5. So my assumption here is error 5 is correct, which, that has a lot of caveats as well, but let's assume that error 5 is correct. Okay, so here are my 45 models, historical climatology of potential intensity. In the northern hemisphere, you have August, September, October seasonal climatology and the historical period. In the southern hemisphere, January, February, March. All the models that have blue, the potential intensity is too low. Wherever you red, the potential intensity of the model is too big. What is obvious that models of the same family have very similar biases. So here you have 3 versions of AC3, Earth3, and then the biases are very similar. Same thing with the INM CMM model, or NUROC, or the MPIs. So they all have different biases, but the final bias within a family of models seems to be very consistent. So that was in terms of one thermodynamic variable, not like a dynamical variable, which maybe we hope that the models will be doing better. So here, vertical shear biases in all the models. Same thing, this is the magnitude of the vertical shear. Red, the models have too much vertical shear. Blue, too little vertical shear. And then you see some different common patterns. For instance, a lot of models have low shear in the Central Pacific. So when you have a projection of the increase of tropical cyclones near Hawaii, for instance, is it because we are really expecting to have that, or because the models start with the biases of having very low shear near Hawaii? We don't know. That's what we have. That's what we have, CMIP6. You can do your Taylor diagram. You can then define some models that have, here is for the potential intensity, have very far from the packet and have big biases. Don't know what to tell you. Always the multimodal mean is the closest to the error 5, whatever you do. Now the vertical shear, the bias is smaller than the potential intensity, but if you zoom in, you can still get some models that have big biases. Okay, so I can do that for all the other variables. CMIP6 models have biases. So one of the things that we do this downscaling that I'm going to talk about, but the CMIP6 environmental fields are the input that we give. So we wanted to deal with that a little better. And why? I forgot that. The other biases that we see is not only the mean, in the variability. So all your models seem to have very low internal variability in potential intensity. So not only the mean, we have biases also in the variability. And similar to vertical shear, we have only a couple of models that have a variability of vertical shear that's similar, or even a couple of them greater than error 5. All the other ones, the variability is way too low. So this is what we use as the input of our downscaling model, is one of the Genesis index. It's the one that we developed in our group. We can use, Carey has 2, Murakami has 1, everybody has their own Genesis index, but whatever. I can't say which one is better because I don't think, they're about the same. But basically, this is the one. It's an updated version of the method we developed in the Tippett paper in 2011, now using error 5, more recent tropical cyclone data. And we use 4 variables, either column relative humidity or saturation deficits, because of this issue of the increase or decrease in the future that I noted before in my original paper. And then potential intensity, vertical shears, and absolute vorticity. So I do the fit. I have a beautiful Genesis index with error 5 that works beautifully. And then if I I have my Genesis index. I apply that to CMIP 6 without doing anything. That's what I get. So you have here in red your error 5, Genesis index, and that's what I did the fit from 1981 to 2010. And then in black you have the observations, and then that I used to fit. And then this is I just did for a subset, this figure, just a subset of 13 models. All of them, because this Genesis index has the characteristics that when we integrate, you have the number of tropical cyclones. It's designed this way. So when I integrate, I have much fewer tropical cyclones in all the CMIP 6 models than we had in error 5 in observation. So what we did a bias correction in the models so that we use the error 5 climatology, and then I just add the model anomalies for each year, and then calculate the Genesis index. And then at least we are in the same ballpark. Then you have the error 5 index. And it's not only the environmental fields. So these are historical simulations. They're tracked by Kevin Hodges using the track algorithm. And here are the models that he tracked. And here climatology. You can immediately notice that it's not only the environmental fields that have problems. If you track the storms in these models, you also have a lot of biases. Not surprisingly, CMIP 6 models are not high resolution, so you wouldn't expect, but you have significant bias in their patterns as well. And if I try to make a relationship between, for instance, the Genesis index and this number of tropical cyclones in those models, we will expect, that's what we want to know. Does the mean number of tropical cyclones in the model is related to these mean environmental fields? So here are our group Genesis indices, and there's absolutely no relationship. In the bottom is Carey Emanuel has 2 Genesis indices. Also no relationship with the number of storms in the model. That's the mean climatology, okay? And, it's, I'm not surprised because I have done that for the CMIP 5 models, plus the hurricane working group models, plus some process-oriented models, and I published in that paper in 2020. We have no relationship. So when people say, oh, the mean model vertical shear is high or low, that's why that model has too few storms. What I'm showing in this paper here, we are not seeing that. in terms of the mean. So if you have high shear in one year and lower shear in the other year, you have more tropical cyclones, let's say in the Atlantic, that the year you have low vertical shear and fewer, the one have fewer vertical shear, higher vertical shear. But if you want to explain the mean climatology, the environment is not explaining that, at least to all these models that I have looked. And in this paper, I did not only Genesis index, potential intense, whatever you want. I could not find a relationship to explain the model climatology. So if you want to say, okay, I want to improve my model, and by changing the vertical shear, that's not telling you that's going to solve your problem. Okay, so what we have so far for the CMIP6 is that the biases, there are big biases in the fields that we use for tropical cyclone activity and that you used for everything, for your tracking your storms or downscaling, whatever you use, they're going to be influence your results. And there are biases in the tropical cyclone proxies that we're using, and bias in terrain variability, so biases everywhere. In spite of that, we use that to do projections. Why not? Everybody does that, so. And then we have things like, here is mean PI anomaly in August, September, October, in the huge, across the models. In the present and here in the future, and then we have one model, will be unnamed, that it's completely out to lunch. If we exclude that model, then we have here, how the potential intensity is changing. This is multimodal mean and the 3 scenarios, and you see what to expect. The potential intensity is going to increase in the future. One of the things I find interesting is you think about the near future. Actually, the SSSP 245 increases faster than the 370, and that's because of the amount of aerosols that the 370 have much more aerosols than 245. And Adam Sobel and I had a paper a few years ago saying how potential intensity is very sensitive to aerosols. Okay. If you now look at the spread of the models in the different scenarios, you see spread seems to be increasing as you go to high emission scenarios. We can also look at, people have looking a lot of model sensitivity, and that some models are, are warming too much, and they're not likely. So that's, I just used based on the transient climate response, how Hausfather decided some models were likely and some not. So the dashed lines here are all models, and if I just use the likely models, I have the lines here. So it does decrease, especially at the end of the century, and especially in the high emission scenarios, but it's hard to see any difference in the near future. How about the patterns? Okay, so here we are, CMIP6, difference of potential intensity, end of the century and then the end of 20th century for 3 different scenarios. Increases most places, decrease in some specific places. Hey, I did the same thing for CMIP5. The pattern is exactly the same. And if you actually look at CMIP3, that Gabe Vecchi has done that, the pattern is the same. So what are we doing with CMIP7? Can't we come up with some more interesting things than do the same things? If you look at the patterns in regional Atlantic, we have the same patterns. So this is the potential intensity difference. How about the vertical shear? Here we have CMIP6 changes in vertical shear. We have like a lot of increase in the Caribbean, Eastern Pacific area, decrease in the near Hawaii, but that's a region, remember, we had a big bias in the vertical shear. If you look now, compare CMIP6 in the Atlantic with CMIP5, Ooh, I would be hard to say that we learned a lot from CMIP 6 compared with CMIP 5. Ventilation index, which is another index that Carrie and Brian Tang came together, which for intensity and formation of storms. And basically when it's low, it's good for storms. And this is what Brian Tang and I had for CMIP 5 in the right, and here in the left we have CMIP 6. Same story. I don't know what we learned here, but we are having the same stuff. As I mentioned, we have two Genesis index, one that increase in the future, one decrease in the future, and that's the patterns of their increase and decrease in the future. You can also see their spread and how they do for the different scenarios. Okay, that's for about the proxies. So to study tropical cyclone risk, and like for instance, I want the risk of tropical cyclones in the region, I need many more storms than I can just running a climate model because we can't afford, because especially land falling, and we want to look at sea level rise, you want to look at combined hazards of storm surge and flooding and all that. So one way to do that is develop a tropical cyclone risk model, and we have done that at Columbia for a few years now. This is another model that was created by Nadia Bloemendaal in the Netherlands. Hers is a totally statistical model, has an increase of storms everywhere, as you can see that in the future. So I'll just try to explain a little bit about our model. So this is our model world, one ensemble from when it's downscaling from the reanalysis. Here is the real world observations, there are tracks. Of course, there are biases. There are no models without biases, especially like from the Central Pacific. But you get your Cat 5s, you get a lot of the right tracks of the storm, and this is just one ensemble of our model. We can usually do a lot of ensembles. We downscale CMIP 5, and I should say, so the way we have this model is like in 3 steps. The first step, we get the environmental fields from the Genesis indices, and that gives me the probability of the storms to be generated. And then we use a statistical a model exactly like Carrie Emanuel has for moving the storm, based on the winds. And then we use a stochastic model for the intensity. Right now, we have also coupled this with storm surge model. We have also coupled this with socioeconomic models using exposure and vulnerability. We have been adding constellation. Now we are working on adding rainfall, as James is also doing with his model. And when we download for CMIP 5, because we use 2 types of Genesis indices, one the column of humidity and one the saturation depth, is we got downscaling either go up or go down, depending if you use column relative humidity index or the saturation depth. So the Genesis index was really determining the frequency of the future in our downscaling for CMIP 5. We can use that, for instance, and look at, for instance, this is a paper that Chang did published last year, looking at the risk of New York State and looking at, here's Cat 1 and how it changes from the historical to the future as mid-century and end of the century. And here Cat 3 is how it affects different regions. So we can really narrow down to certain regions and look at the changes. Almost done. And if we did now for CMIP 6, for 13 models now, we're basically getting very similar results. Our results are very depending of which in Genesis index we use. So what can we do? Right now, we're trying to look if we can use the historical data to really tell us which is the more scenario that we really think is going to happen is the Genesis index with the column relative humidity or the saturation depth. You can, do that. Or the other approach that I'm working with Dan Chavez from Purdue is try to have a more theoretical based Genesis index, not so much based on statistics. Or, people say machine learning is going to solve. It's still doing the same data and still statistics, so I'm not sure. Okay, I'm still working with biases with, probably all of you know that the mean Pacific trends have a lot of issues, and basically they have more La Nina state in the future in the historical observations, while in the all the models are more El Nino-like state. And we just have this paper that, now it's accepted, going to appear in PNAS talking about the implications of that for tropical cyclone projections. Because if you have the wrong state in the Pacific, mean state, that will also affect your projections. Just to finish, that was the mean Pacific state. All about the ENSO diversity and how well the variability of ENSO is. And then Christina Patricola has this very nice way of separating models and telling if the model has too much diversity, too little diversity, or the right amount of diversity. And so here is what she got for the Sim6. Happy to explain how we do it. And what was interesting that I got is that our projections of how the ENSO relationship is different depending if your model has too much diversity, right amount of diversity or not. So all the environmental fields that we use, they have different, so here's your historical ENSO relation composites, and if you see all the 8+ model, the one that has too much diversity, have a very different projections of the ENSO tropical cyclone relationship in the future than they have for the A models and B models. So I'm running out of time. So basically, we have all these issues that I talk about, the main biases, but we have other ones that we have to think about too. How the Pacific mean bias is affecting the relationship. And that will affect not only tropical cyclones, everything that's affected by ENSO. If your CIMIP6 models are doing something wrong with that, in terms of the mean Pacific bias and also in terms of the ENSO diversity, that will have lots of impacts on our projections on tropical cyclones and everybody else. I hope I was not too negative in my talk, but thank you very much.
Thank you, Suzana, for very interesting, although a little bit pessimistic historical overview and seminar. We have some time for some questions. Any questions from the audience? Jamie?
I was interested in the humidity versus deficit differences, and I wasn't sure I caught which direction they go. Is the humidity is decreasing and the deficit is increasing in the future? Or can you see anything?
So the relative humidity increases, but very little because it's the ratio of the two quantities, while the saturation depth is decreasing a lot. Okay. So because the Genesis index has these coefficients, in the so you have the potential intensity, which is increasing in the future, and then you have the humidity. So if the humidity is not balancing the potential intensity, then you're going to have an increase. And if you have now the saturation depth is pushing it down, then it's going to lead to a decrease. But of course, this depends on the Genesis index you use. Carries that he used not saturation depth, he used entropy depth, and he has different coefficients, different exponents, and he doesn't get a decrease using entropy deficit. That's why it's tricky to think about that using all these proxies.
So the deficit is more related to the absolute moisture difference.
Yes, yeah.
So that there must be some clue there.
Yeah, that's what we're trying to think about, but have ideas, happy to hear.
Any other questions in the room? Yes.
Great talk, Suzana. The potential intensity biases looked big one way or the other. From my understanding, potential intensity is sort of set by CAPE and SST. Do you have a sense of which of those broad parameters is kind of responsible for those huge potential intensity biases in the CMIPS models?
I think for answer, I would have to go model by model. I'm not sure that you can have that for one model. You know, I did not look individually in the models to see it there. That's a good suggestion.
One more question, James.
Yeah, thanks, Suzana. So just thinking about the CMIP6 biases in the historical shear. So Clara Dessa showed in her 2012 paper that 50-year trends in circulation can have a large internal variability component. So is it really a bias in the historical CMIP6 shear? Should we want it to replicate the observations?
So I used all the ensembles that I have for all the models. And like the Canadian model for the historical, I think they have like 65 ensembles.
Oh, okay.
There are some models that were like 5 ensemble members, but there were some that have 30 on the access had like 30 ensemble members. So they're, you know, they are not, I'm not, you know, I use all the ensembles that I had on purpose.
Yeah.
So I'm not sure that that could explain it, at least for the models that have a reasonable number of ensembles.
Okay.
I'll use my privilege to ask hopefully a quick question. So if the models are not getting the disease or the large-scale fields right, what are they getting right?
I don't know.
Okay. On that note, okay, one more question here, and then while I walk, I remind you, you are all welcome to stay for the post-seminar social.
So I have a very specific random question. In your time series, historical time series of, I think it was Genesis Potential Index, there are some stark drop-offs.
These are
1880
volcanoes.
Okay, I had assumed so, but yeah, thanks for clarifying.
Okay, so you're all welcome to continue the conversation over coffee, tea, and cookies, and water. Suzana is here until tomorrow, and she has some time to meet tomorrow. So if you would like to meet with her tomorrow, let us know. Thank you so much, Suzana, again, for an interesting seminar, and thank you all for coming.